So this lesson is going to basically concentrate on sinusoidal models. Not all of them are going to, we're not going to be using a sine function within our model every time. Basically, we're just going to be using whatever makes the most sense for our problem. So the trick is for our sinusoidal models is to recognize all the key attributes of our function. So it's going to be kind of like our worksheet where we were building functions, but this is going to have a real-life application. So they're a little trickier by nature of that. So this first example here is a Ferris wheel question, which we see a lot on sinusoidal models. And it says, Rashad rides a Ferris wheel. His distance from the ground varies sinusoidally. So right there's a dead giveaway that we should be using a sine function. Let me get my marker working. A sine function as far as like what I'm going to set up. So when the last seat is filled and the Ferris wheel starts. Rashad's seat at the position shown in this figure, so there he is, boom. Let t be the number of seconds that have elapsed since the Ferris wheel started. And then Rashad determines that it takes him 3 seconds to reach the top. So right there, that's a clue. 3 seconds for him to reach the top, which is another way of saying the maximum or the top of our range. And that is 43 feet above the ground. And then he also determines, and the 3 seconds is going to be important to us in a moment. It also determines that he is back to the original position after 8 seconds. So one revolution takes 8 seconds. That is a way of saying, let's see, that's the period length, right? Yeah. I always get period and frequency reversed in my head because my dyslexia and all that. I got to think real hard. All right, so the period is 8 seconds. The diameter of the wheel is 40 feet. That's not a direct clue to our equation, but it is going to help us find parts of our equation. So if I go to my picture here, if you want to think about it this way, where are we at? The diameter of this wheel is 43. Oh, no, it's not. It's 40. Hello, Bruzo. It's 40. But it said the max height here is 43, which tells me that there's the distance, obviously, between the wheel and the ground. And the distance right there is 3 feet. So it can't hit the ground for obvious reasons. Otherwise, the whole wheel would fall apart. So if you want to think of it this way, I like to graph before I come up with the function. The bottom of my sinusoidal range is going to be at 3 feet. And the maximum is going to be up here at 43 feet. So the clue of the diameter being 40 feet is basically the range of the from max to min, or min to max, which helps me find a couple of things. Just it makes sense for the problem, but also I can find my midline either by visual acuity, or I could do the midline formula where I add them together and divide by 2. So that's 23, right? It's 46 divided by 2, yep. So this is a little confusing because we're not starting at the bottom of the wheel, which if you remember your Algebra 2 problems you used to do, it's like every time we did this, we started at either the top or the bottom of whatever the sinusoidal graph was. So this time, his cycle, if you want to call it that, is going to start when he's kind of partially above. He's in the middle of the Ferris wheel, basically, or at least the arc of it. So he starts, like, you can start the function wherever you want. What if we started it at the top? So what if we said right here, he reaches the top after 3 seconds. So if I want to label this marker here, this is 3 seconds into his little trip. And then his graph is kind of going to do something kind of like that, right? There's some other clues, though. This is 3 seconds. He reaches the maximum. And then he's back to his original position after 8 seconds, which is a clue for the period, but I'm not going to put it on the graph here because it's not going to make tons of sense, though, right? However, what is going to make tons of sense for me is this point right here. He has a period of 8 seconds, right? So this is 11 seconds right here. So, oh man, I realized I lied to you. I told you this was going to be a sinusoidal graph. What we're actually going to do, instead of calling it sinusoidal graph, because look at the shape here. It starts at the maximum. So what if we said this is like a cosine graph that's been shifted? That would make more sense for us. Now, is this the only way we can write the model? Absolutely not. If you want to call this a sine graph and you want to figure out if you kind of back up the function here where it would start at the middle, you could call it a sine graph, but it's not going to make sense for us. I know that the period length is 8. Hello. I actually think I'm ready to write the function. So they labeled it h of t, the height with respect to time, where t is measured in seconds. And the amplitude measures the distance from the middle to the max or the middle to the min, and that is going to be the radius of the wheel, obviously, so that's a 20. It's a cosine that's been shifted to the right a little bit. So cosine, and then the b value, remember b is 2 pi divided by period. So if the period is 8 and I reduce that fraction a little bit, the b value could be called pi over 4. Now I'm going to leave it in what we call factored form. T, remember how it's been shifted to the right a little bit, a phase shift? So it's been shifted right 3 seconds. So I'm going to say t minus 3 seconds. And then the midline is plus 23. So that looks a little crazy, but that is the function. At least it's a function that we could use. Let me get my face out of the way. The next thing we're going to do is we're going to take this function and we're going to be using our graphing calculator to do some predictions. So we're going to get that function typed into y equals. We're going to change the t variable out for an x. Go ahead and pause the video if you need to, because I already have these functions typed in. So on my screen, you're going to see a whole bunch of functions because I took the liberty of typing in every single function I'm going to need for this lesson. And then what I did is I de-emphasized the equal signs, which is another way to turn off the graphing utility for that particular function. So when I do some window work, I'm only going to be graphing that first 20 cosine of pi over 4 parenthesis x minus 3. Make sure you close double parentheses there, and then plus 23. So, I had a visitor. Okay. So when I play with the window a little bit and zoom trig, I'm only going to be graphing the function that I'm actually talking about today. So what I would like you to do is, let's go to mode for a moment. We have to think about what mode we have to be in. And I'm measuring in radians. So can you make sure that you too are in radians? And then after that, I'm not too worried about it. As far as the window goes, though, gosh, the face is always in the way. Remember, x represents time. So if I think about how long we're going to be on this Ferris wheel, I don't think it makes sense to go to negative 10 seconds. So let's go 0 to, let's see, I'm going to have to predict some weird times coming up here. So let's go 0 to 12. Actually, you know what? Take that back. 0 to 11, because wasn't that the end of our first, cycle? And if I look ahead in my paper here, I don't need to go too far out in my prediction. For my y's, I don't really know. Well, I do know. Sometimes I don't. But remember we graphed it? Wasn't the Ferris wheel, 43 was the top? So what if we went to y minimum? And I started at 0, even though the Ferris wheel doesn't hit the ground. Let's go ahead and say 0. And then for our maximum, it was up at 43. So I'm going to give myself a little bit of wiggle room, though. I'm going to say 44. Okay. Now hit graph. Oh, that's lovely. Okay. So keep in mind what we sketched earlier doesn't quite match what we see on our screen here because of the, we started our function at that right shift. So we actually started our function right here. And then we kind of graph from here to here. But what we're going to do now is we're going to use this function. We're going to predict some values. It says when t equals 6. So you have a choice. You could either go to your table, or you could just hit trace, and then 6, and then enter. Not 66. Lovely. Go to. Try again. 6. 1, 6. There we go. Enter. And the height at 6 seconds is 8.86, roughly. 8.9, I think it says. This is what I rounded to, is the 10th. So 4 1/3, you could type literally 4 plus 1/3, or you could do 4.3333, whatever. And this is how we're going to find the prediction values. I usually use my graph because my table is not usually set up in ask mode, but that's up to you. All right. So sorry, I kind of fumbled through the beginning of that. My bad. Let's take a look at, oh, that's cute. All right, the next question. We have a physics question here. A spring with a weight attached to it, so it's going to be bouncing up and down. And the way it bounces is technically a sinusoidal model, but as we saw in the last question, if there's any phase shifts, sometimes we consider it to be a cosinusoidal model, simply because of the shift and where we want the problem to start for time. So if we start reading some clues here, it says the distance from the floor varies sinusoidally. So again, it's telling us it's a trigonometric function. And you start the stopwatch. When the watch reads 0.3 seconds, the weight reaches the high point of 60 centimeters. So this is another one of those at 0.3 seconds, which this is counting by tenths. It's going to reach this maximum line up here, which apparently is 60 centimeters. So this is going to be another one of those. It starts at the top, so even though they said it's sinusoidal, we're going to use a cosinusoidal graph, and it's just going to be phase shifted over to the right a little bit. And then there's some other clues, I'm sure. The next low point is 40 centimeters above the ground, so there's the low line, the minimum, and it occurs 1.8 seconds. So that'd be like right here. All right, so lovely as usual. Okay, so we have a cosine graph that's been phase shifted to the right. It's been stretched out quite a bit here. But if we think about what would happen here as far as like what that means for the period, think about how long it took for the graph to go from here to here. This is 0.3 seconds, and this is 1.8 seconds. So that's a distance of 1.5, but that's only half the cycle. So the period is actually 3 seconds long. So let's see here. What else do we need? I think, as soon as I find my midline, I think I'm okay. Ooh, let me pause. All right, had a little pledge action there. All right, so our midline is halfway between 60 and 40, so that would be at 50. And then I can see that my amplitude is a distance of 10. So we're going to have a cosine graph that starts at the max, so it's a regular cosine graph that's been shifted to the right 0.3. If I want to write down all these clues, that's fine. The period is 3 seconds, which means if I go to calculate the b value, remember that's 2 pi over the period, so 2 pi over 3. The phase shift is to the right 0.3, so it's going to be a x or t minus 0.3 when I put it in the formula. Amplitude is 10. Midline, the k, is 50. All right, let's do this. So we have a amplitude first, 10. Pen's failing me. All right, and then we decided we're going to call this a cosine function because of the nature of it beginning at the maximum. The b value is 2 pi over 3, and we'll leave it in factored form. They want me to use t instead of x. Shifted to the right, so t minus 0.3. Double close your parentheses there. And then my midline is actually at a plus 50. All right. So same thing. We would go to the calculator, and we would type this function in. We're going to be using x instead of t. So, like, remember mine already had all the functions typed in, so I would de-emphasize the old function, emphasize the new function, call this x, though. And then I want to know what's the distance off the floor when the stopwatch reads 17.2 seconds. And then when you first started, so that would be like t equals 0 or x equals 0. So what I would suggest is that you first, before you even bother looking at the graph, that you change your window to be appropriate for the problem here. It wants your first prediction to go all the way out to 17.2 seconds. So for your x's, I would go from like 0 to 20. And then if you want, you could zoom trig this and see if that works for a window. Otherwise, your y's are pretty obvious, huh? Because they toggle between 40 and 60. So if you want to go a little above and below, you can go 30 to 70. That's what I would do. So it's up to you. Just for a little heads up, when you do this on your calculator, and if you're practicing this, please pause the video and try typing this in and finding these two values. But you should get an answer here of 43.3 centimeters. And then here you should get an answer of 58.1 centimeters. All right. Oh, that's lovely. I don't know what I'm looking at. Oh. Ocean currents. Fascinating. Okay, so a tsunami, a tidal wave, is like a rapid change in tide. And it creates those big, lovely waves that demolish towns. So it's a fast-moving ocean wave caused by an underwater earthquake. And the water first goes down from its normal level and then rises an equal distance above its normal level and then returns back to normal. So it definitely has a sinusoidal approach to it. The period is 15 minutes. That's an important clue. And suppose that the tsunami with an amplitude of 10 approaches a pier at Honolulu, where the normal depth is 9 meters. So this is going to be like our midline, okay? Assuming that the varies sinusoidally, blah, blah, blah. Okay, so if I'm thinking about what the sketch looks like, because I think that's the most important part of this problem, is to actually sketch it out. Our normal ocean depth here at the pier is 9. It's got an amplitude of 10. So it's going to go down to -1. I should have made this smaller, my bad. And then up here to 19. And it does say that it's something about it starting, the water first goes down from its normal level, so it kind of like reverse swells. So it's going to start down here, and then it's going to do one of these. And again, it said sinusoidally, but sure does look like we're looking at a... Oh, for Pete's sake, Abruzzo. This is not what you read. I think I need a break, guys. Okay. Starts at normal level, then goes down. There we go. So in this case, it is going to be a sinusoidal graph. However, because it goes down first, stellar graph as usual, it's going to be a reflected sinusoidal graph. So the amplitude is 10. We know the period, which means we can calculate the b value to be 2 pi over the period, which was 15. And then there is no phase shift this time, so we don't have to worry about that. The midline's 9. I think we're ready to rock and roll. So amplitude is 10, however it is reflected. So -10 because of the shape. Let's call it a sinusoidal graph. Now, if you really wanted to call it cosine, you could have. You just would have had to figure out what this point is right here. But let's not do that. The b value is 2 pi over 15. They want me to use t. If you want to change that to an x, that's fine. And then our midline is plus 9. So same idea. We're going to go to our calculator. Go ahead and pause the video and get this typed in, please. And you're going to replace that variable with an x when you go to your calculator. As far as window goes, again, you can try zoom trigging and see if you like that better, but if I look at my predictions 2, 4, and 12 minutes out, so I'm going to make my x's go from like 0 to 15, and my y's, -1 to 19 is the range, so how about we go -2 to 20. So pause the video, find these values if you're practicing on your calculator, but I already did this, so 2 minutes in, it's a height of 1.6 meters, 4 minutes in, it's a height of -0.9 meters, and then 12 minutes in, it's 18.5 meters. So according to your model, what will be the minimum depth of the water be? So that would be the bottom of the range there, so it's -1 meters, which is kind of weird to say, but in real world contexts, it is 1 meter below sea level, because 0 would be considered like sea level. Normally the pier, they said the ocean level is 9 meters from sea level, so -1 means 1 below sea level. And then the wavelength is the distance from the crest of a wave travel in one period. Okay, so it's also equal to the distance between 2 adjacent crests. If a tsunami travels 1,200 kilometers per hour, what is its wavelength? So for this question, we have, let's do a little dimensional analysis. We have 1,200 kilometers per hour and 15, the period length is 15 minutes, right? So we have a dimensional analysis issue of like, we don't have the right label. So I need to convert this into kilometers per minute. So in 1 hour there's 60 minutes. So if I do a little math here, that becomes 200 kilometers per minute. And then 15 minutes, right, was the length of the period. So the rate is 200 kilometers per minute. The time is 15 minutes. So if I take 200, sorry for the sloppy handwriting, multiplied by 15, I get 3,000 kilometers. Oh boy. All right. Let's see. Extra credit opportunity. Nah, maybe not. All right, so there is one more question. Oh, there it is. I missed it. We have a rocket. When a satellite or a rocket is launched into the orbit, such as Cape Canaveral launches things all the time, right? Which is not on the equator. It goes into orbit that takes an alternately north and south. Okay. Its distance from the equator is approximately a sinusoidal function. Suppose the satellite is fired into orbit from Cape Canaveral, and then 10 minutes after it leaves the Cape, it reaches its furthest distance north, so that would be like a maximum of 4,000. So 10 minutes later, so this is one of those that's going to be shifted to the right. So we're going to have a shifted cosine graph. It's been phase shifted 10 minutes to the right. So if I kind of transfer that over here, 10 minutes in, it's going to reach this maximum of 4,000. After, let's keep reading. Half a cycle later, it reaches its furthest south distance, which is 4,000. No. Oh, also 4,000. So we're going to call that negative 4,000, huh? Because we'll say the equator is line 0. All right, so down here, half a cycle later, completes one orbit every 90 minutes. All right, so right there is the period. Now, remember, this was just the half cycle, so this is like 45 minutes later. So if you want to label it, this is at 55 minutes. I don't know how important that is to you, but other than like using our calculator later. All right, so let's write the model in terms of y this time, and for y in terms of t. Again, when you use your calculator, you're going to be using x instead of t. So this graph, which I don't even have a complete cycle done, but something like that, has an amplitude of 4,000 and then starts at the top. So we're going to consider this a normal cosine graph. So 4,000 and then cosine. The period is 90, so the b value is 2 pi over the period, which if I reduce that, that'd be pi over 45. Now I'm going to leave it in factored form because there's a phase shift. So let's call that t, and then shifted right 10 minutes, so minus 10. And then there's no vertical shift because the equator we're going to call 0. So similarly, we're answering questions off of our calculator. So pause the video and get this typed into your y equals menu. When you go to set up your window, however, your t or your x, let's see, I got to predict all the way out to 163. So let's go like, and they do want something about 0. So let's go, oh, we might have trouble with, well, whatever, 0 to 170. And then for y's, this is kind of goofy. Negative 4,000 to 4,000 is fine for now. What I suggest you do, though, is for your counts, don't count by ones. I mean, it doesn't really matter for what we're doing, but you might want to count by like hundreds or something for your tick marks on your y's. You might want to count by like 20 or something for your x's. But pause the video, get this graphed in, please practice. And I already got these answered on my calculator, so when the time is 25 seconds in, it is, oh, minutes, excuse me, minutes. It is 2,000 kilometers. At 41 seconds, it's below the equator, so negative 2236.8 kilometers, excuse me. And then at 163 seconds, it's negative 1236.1 kilometers. And then when time is 0, that would be when the rocket or satellite was launched, and that would be from Cape Canaveral. So using our model, it comes out to 3,064.2 kilometers, but remember, we're kind of estimating because this is an exact measurement that we're using here. But they know that Cape Canaveral is actually 3,154 kilometers from the equator. So if you know, I know it's not like walking distance close, but if you think about our model, we're really not that too far off. So, and that has to do with like how often we truncated decimals in the measurements, and then how accurate were their measurements for the how far above the equator everything was for our model. So in the 10 minutes, like I'm sure it wasn't exactly 10 minutes. They weren't measuring it that closely, you know? All right, anywho, that's a good intro lesson on trig modeling. So moral of the story is you find all the key features, You decide what type of trig model you want to use. Is it looking like a cosine or sine graph more accurately? Where do you want to start your time? Because that's the start of your cycle. And just remember, there's not always just one obvious answer. Your neighbor might have a different sinusoidal or cosinusoidal model, and we just have to kind of